welcome back. It's a pleasure for me to introduce you Juan Avendano from Aalto University. And he's gonna talk about two-person neuroscience with MEG hyperscanning, insights from a mirror game paradigm. So Juan, please, the stage is yours.
Thank you very much. Thank you very much to you and to the organizing committee for the invitation. It's great to be here and to be back to Italy, at least virtually. Today I'm going to talk to you about this two-person neuroscience study we have been doing using MEG hyperscanning to study interacting dyads performing a mirror game task. This is a work that we have been doing with Ray Tahari, Lauri Parkkonen, and the Neuroimaging Methods group at Aalto University. Human evolution has shaped us as social animals who are continuously immersed in social interactions, at least when we don't have a pandemic around. And these social interactions in real life are quite complex and dynamic. Here at the bottom, we see some schematics of action perception loops. So when an individual is interacting with the environment, this person would get some information through the senses, contrast that information or contrast it with some predictions that the person makes based on past experiences. And by that comparison between the predictions and the information gotten through the senses, this person would decide how to act. But if we add another person to this environment, the action perception loops of the two individuals will become linked. Then one person will become the input of the other person and vice versa. But it gets more complex than that because they are not only reactive. They would be constantly making predictions about themselves and about the other person during the interaction. And this makes the interaction quite complex, dynamic, rapidly changing, and even unpredictable sometimes. So in order to capture the full pictures of these kind of social interactions, it has been suggested that simultaneous brain imaging from the two interacting subjects would be needed. Another aspect that I wanted to mention is that we typically are engaged in the interactions and rather than being passively observing the world around us with other people. And I mention this because most of the research done in neuroscience has been performed on isolated individuals sat in front of a computer monitor, watching very artificial controlled stimuli and performing very well controlled experiments. But the interaction part, that interactive nature of interactive aspect of human nature has been lacking from most of this traditional one-person neuroscience research. To the point that it has been suggested that even in social neuroscience, social interactions are a dark matter. We see from this nice summary from Pfeiffer et al. That the more dynamic an interaction becomes, the more engaged the individuals are in an interaction. And the more individuals interacting are part of the interaction, the more unexplored this aspect of the interaction has been in the social neuroscience field. So taking together all these things I've mentioned before, in the last decade and a half, a shift towards studying two interacting brains simultaneously has been encouraged, with the hope that this would bring us a deeper understanding about how the brain works in social interactions, at least further insights than those that we could get with the traditional one-person neuroscience approach. And the first step in order to be able to measure the brain activity from two individuals while interacting is to have the technology that would allow us to do that. That technology already exists and is known as hyperscanning. The term was coined by Ray Montague in 2002. It refers to the simultaneous measurement of brain activity from two or more individuals. It is available in most of the non-invasive neuroimaging modalities, EEG, fMRI, FNIRS, but today I'm going to focus on MEG hyperscanning, which is the one we use in the data I'm presenting to you today. The first MEG hyperscanning setup was developed at Aalto University. It's summarized in these two papers by Pamela Baez, Andrei Stanov, and colleagues. And this system allows us to measure MEG activity from two individuals who are able to communicate using an audiovisual internet link connecting two MEG laboratories in different geographic locations in the world. This is how it looks like. We have one person sitting inside an MEG scanner in one laboratory, watching another person sat in another laboratory in a different geographical location. They can see each other's upper body and can communicate through audio and video. The computers at these two sites are synchronized, well, the clocks of the computers are synchronized through GPS. So accurate time stamps of all the relevant events are recorded and used to synchronize the recordings offline for further analysis. So we use this MEG hyperscanning setup to try to extend our understanding of real-life social interactions, we use it combined with an adapted version of the mirror game paradigm proposed by Lior, Noy, and colleagues in 2011. And the mirror game is an improvisation exercise where one person moves and the other behaves as a mirror with or without a designated leader. Here is an example of the setup that Lior, Noy proposed. In this case, two persons are moving these candles in the horizontal axis, trying to create interesting movements to improvise together. We use these two, the MBA Hyperscanning setup and the mirror game paradigm together to try to understand a bit better the neural and behavioral signatures of action observation, leader-follower coordination, and joint improvisation in interacting dyads. So I mentioned that this is an adaptive version of the task. So in this case, the participants perform a mirror game in one dimension, moving only the index finger. Is a vertical dimension. The participant is instructed just to create interesting movements, to improvise, is asked to freely change the range and speed of motion as he or she wants, but as long as the movements that are proposed are easy to follow, because there would be another person mirroring the movements in the other side. While the participants do that, we measure MEG from the two individuals. And in this case, one person was located at Aalto University in Finland, and the other was in the Erasmus Hospital in Brussels, in Belgium. And apart from measuring the MEG from the two persons, we monitor the kinematics using triaxial accelerometers placed on the index finger. We had different conditions in this experiment. In one of them, one of the participants will behave as the leader in the interaction. This person would just move without caring about the other person, and would create movements as long, as he wants, as long as these are easy to follow. And the other person would follow the movements proposed by the leader and would try to become as sync with the leader as possible. There is another condition in which they would be asked to create interesting movements together, to try to be as synchronous as possible while improvising. An additional condition was this one, where they were moving, but they could not see each other. So it's more like a control condition. And of course, there was also a resting state where they would just watch a white cross in front of them. Today I'll focus on these two, the leader follower and the synchronous condition. We had 3 trials per condition. In this case, in this kind of asymmetric roles, we had 3 trials when the participant in Finland was leading and the one in Belgium following. We have other 3 trials when the participant in Belgium was leading and the Finnish one following. But for this joint improvisation condition, we only had 3 trials. This imbalance will be a bit relevant afterwards. And we tested 16 dyads, but I'm not going to show you the data from all of them now. We're still working on some of them. And this time we have been doing some work. This is all very preliminary. And today I'm going to show you some bits of these 3, some aspects of the kinematic data analysis, from single brain MEG source level power estimates, and one attempt to use 2 brain data together to classify different interacting conditions. From the behavioral side, this is one example of the kinematics from one trial for one dyad for one of the conditions. This is the accelerometer data after some pre-processing, after applying PCA and retaining the first principal component. In this case, the blue trace refers to the kinematic data for the person in Finland, and the orange one to the kinematic data from the person in Belgium. In this condition, they were asked, that they were told that the Finnish person would lead the interaction, the movement. We can clearly see that from the data, since the blue signal is constantly, for most of the time, preceding the orange one. And this is a clear sign that the person in Finland is leading the movement. These are the phases of the signals above. This is a distribution of the phase differences between these 2. And this is better summarized in this phase locking vector, showing consistent phase differences in one direction, in this case, showing the difference in the lags between the 2 individuals. This is another example trial. In this one, the dyad was told to move in sync, to improvise together. And that is evident from the kinematic data and is nicely summarized by the phase locking vector here with a high phase locking value pointing towards 0. This is the data for the rest of the dyads, all the dyads together. In blue, we see the phase locking vector when the participant in Finland was leading the interaction. In red, when the Belgian participant was leading, so the Finnish one was following. In black, when they were moving in sync, and in green, when they were moving but could not see each other. From these plots, we can see that the synchronous condition, the one in black, although it's not showing a perfect synchrony, it is quite consistently in between the other two, which is a sign that the participants were actually assuming the roles that we asked them to assume during the interaction. Here we see the phase locking values at the group level. Each line represents the mean for the group with 95% confidence intervals, and the dots are the phase locking value for each dyad. We see that for the 3 interacting conditions, when they were leading, following, or sync, they had a similar synchrony in the movements, but the synchrony dropped when they were moving without seeing each other, which is expected. This is the signal frequency of the accelerometer data. And here we just see that for the interacting conditions, they move with a similar frequency, but when they don't see each other, they move slightly faster. We did some analysis on the MG data. Specifically, we computed the MG source level power estimates for the delta, theta, alpha, beta, and gamma bands. And we computed the mean of this over 400 parcels according to this parcellation proposed by Schaffer et al. In 2018. We compared the power across different experimental conditions, specifically between leaders and followers, leaders and sync, and followers and sync. But now I'm going to show you only those that were statistically significantly different across conditions. For the theta band, we have the raw power for the leader, for the follower, for the left hemisphere, for the right hemisphere. Here the differences across conditions and the parcels that were significantly different across conditions according to some permutations. We see that we have mostly some theta differences in somatomotor areas, and this actually showed a stronger theta power for the followers than the leaders in those areas. For the beta band, we found a couple of parcels that were different across conditions, and these were located in the superior parietal areas and also showed a stronger beta power for the followers than the leaders. Now, what does this mean? We are not exactly sure yet. There could be a potential link to behavior. The closest findings in literature are these two shown over here. This is a study by Guillaume Dumas and colleagues that found a stronger theta corticomotor coherence in somatomotor areas for cell movements when coordinating with a virtual partner that was a generative model of movement coordination. And this one by Zhou and colleagues that showed a stronger phase amplitude coupling between the kinematics and the posterior beta activity in followers and leaders. So it could be the case that the modulations in theta and beta that we found here could be mediated by behavior, and perhaps they're related to a differential kinematic processing between leaders and followers, but we need to do further analysis to properly understand what's the meaning of these differences we've obtained. Then we try to use the data from 2 brains together to try to extend a bit more our understanding about the brain in this social context. We try to use this data to classify different interactive conditions, in particular the condition where they were in a leader-follower interaction versus the condition where they were moving in sync. And this approach was inspired by this study by Ivana Konvalinka and colleagues. I use a very similar approach, also using the data from 2 brains to try to classify different kind of interactions. So we have merged brains now. So we have 800 parcels, 400 per brain that we use as features. For each of those parcels, we computed the mean power in moving windows. Each window was 1 second long with 0.5 seconds overlap and was normalized respect to the power in the resting condition. We used 3 different types of inputs for the classification. Imagine that each of these rectangles is one matrix that we use as input for the classifier. The blue ones would correspond to the Finnish brain, and the red ones would correspond to the Belgian brain. These are the labels for the two classes. So the leading and following interaction, the synchronous interaction. This would be the brain number 1 that changed from leading to sync across the classes. The brain 2 that changes from follow to sync. So if you remember well, it's mentioned that we had 3 trials for this condition when Finland was leading and Belgium was following. We had 3 trials when they were in sync, and 3 trials when the Belgian brain was leading. So I tried to arrange that a bit to use 3 different inputs, keeping something constant. That was the fact that the brain number 1 would be the brain that would change from leading to sync, and the brain 2 would be the one that changed from follow to sync. And this other input is simply like uses the whole trials, keeping unbalanced classes. The classifier was a simple logistic regression. We had 2 different models with L1 and L2 penalties, and a default hyperparameter C = 1. We use a recursive feature elimination algorithm with cross-validation false. This algorithm would keep like iterating, eliminating features till it finds a set of features that would provide the best classification accuracy. And we left out 20% of the data as a validation set. Considering that, well, moving in sync will be mostly following the other person, and that both follower and those dyads moving in sync would wake more the other person behaviors, and the leader that would make more sound behavior. We expected that the brains from the follower and the lead and sync participants would be more similar, and then perhaps the brain of the leader would be the one driving mostly the classification, but this didn't happen. These are some examples of the classification results. I think I lost my mouse. Oh no, it's back. This is the accuracy in the validation set for the logistic regression with L1 penalty, with L2 penalty. For the 3 different inputs that I showed you before, we can see that the accuracies are above 75% for all cases, which is good news. And now this is the, well, one of these is one of the dyads. For each of these dyads, for each of these different inputs and models, the recursive feature elimination would select a set of features that would be the optimal ones for the classification or give the best accuracy. We computed the probability that a feature would have to be selected across all the dyads. This is summarized here. We see here the top features probabilities for the first brain, for the second brain. This one, when they use this kind of input with the L2 penalty, was the one that provided the most consistent features. And this is the one I'm going to show to you in the next bunch of results. These are the features that were selected for this model, and that were selected over 75% of the time across the different dyads. You can see some activation, well, there's some features in the parietal areas, in the prefrontal areas, but we are actually still trying to understand what do this mean. What does this mean? For the theta band, we see again that the accuracies are over 70% for all the cases, but still the pulses that were selected are quite scattered around the brain, so we're still trying to understand their meaning, and the same for the alpha, beta, and gamma bands. Another interesting, potentially interesting finding in our data is that these classification accuracies correlated with behavior in the beta and gamma bands. With behavior, I mean that the phase difference in the movement between leaders and followers, and the phase difference in the movement between the 2 same individuals in sync, correlated with the classification accuracies for those 2 interactions, at least for in the beta and gamma band. But we are still trying to understand the meaning of this finding as well. We went further and used all the data from all the participants together as input for the classification. We got accuracies about above 73% for all the frequency bands on the validation data, but the interpretability challenge remains open. So as a summary, we have some good news from this data, is that the finger kinematic agreed with what we instructed to the participants. We found some modulations in theta and beta power, showing stronger power for followers and leaders, but we need to follow up this finding. We got that the two-brains data provides information to reliably classify the leader and leader-follower interaction against the synchronous one. And we obtain high classification accuracies even with this simple classifier, and even a potential link with behavior. But still, interpreting the findings remains quite challenging, especially for the two-brains data when using machine learning. So some final remarks. If you want to do two-persons neuroscience, the technology is available, which is great, but the physiological and psychological interpretation remains challenging. We need to get some methods, paradigms to get the most out of it. And it is still not clear what would be the ideal sample size to get meaningful information out of this rich data. So further work is needed to arrive to which extent these two brains data can provide insights into the neural correlates of real-time social interaction beyond those that we could get with one-person neuroscience. I would like to end with a quote by Rita Hari, that I saw in a YouTube video a couple of weeks ago. So she said that some people say that the brain is the most complicated system in the universe. Now think if you take two brains. But I think it's a beautiful challenge worth all the time and effort that has been invested in it and more. And of course, it wouldn't be possible without the great effort that a lot of smart colleagues did in the past. So I would like to thank all the colleagues that work in developing the MG hyperscanning setup, the colleagues that work in this data I show you here, and those that contributed with experimental design and data collection, and some that did some initial data analysis steps. And of course, thanks to Rita Hari, Lauri Parkkonen for leading all this amazing effort, and to the Neuroimaging Methods Research Group at Aalto. Thank you. Do you have any question?
Thank you very much, Juan, for this very nice talk. I would say, I guess it's even more a mess if you start in taking a group of brains and not just two. So,
yeah, completely agree.
Like I said, let's see if there are any questions from the audience. If not, in the meantime, I have actually two questions. The first question is if you have tried to correlate, because in the last slides you have shown the correlation between the results of the classifier and the behavioral data. If you have done something like that also for the first part of your analysis, when you compare the brain activity, leader versus follower, if you have checked if, for example, you see more differences in the dials that had a greater delay in the behavioral data. I don't know if you got my question.
Okay.
I mean, in the pitch.
Not that exactly. That could be interesting to check. We haven't done that exactly. We are working on correlations between behavior, like the norm of the accelerometer data, and the MEG envelopes.
Okay.
Try to say, but not that specific difference, and that could be interesting to check. Yeah.
Okay. And the other question is that this is more like a curiosity. You have used the wall trial in the MEG data to do this analysis. So if you have a trial, you consider the wall window, and may it have sense to consider a shorter window, for example, to prevent the fact if the two persons after a while have started moving coordinated one with the other, because maybe they adapt to the movement of for example, the follower adapt his movement to the leader, and so maybe with time their behavior may be more similar at the end with respect to the beginning of the window.
Yeah, I think that's one of the potential future directions. Since this is a very dynamic data, studying it in a dynamic way would probably give us much better insights about what's actually going on. But yeah, I haven't done that yet.
Okay, good. Let me check if there are other questions from the audience in the meantime. It seems no, so thank again to Johan, your talk up from Italy, not
Thank
from
you very
Rome,
much.
but okay.
Grazie mille.